Hey everyone, in this video I'm going to walk you through this paper and summarize it for you so that by the end you'll understand exactly what this research is about without having to read the whole thing yourself. Let's start with the title. This paper is called Adaptive Finite Time Tracking Control of Fractional Microgrids Against Time Delay Attacks, published in IEEE Transactions on Industry Applications 2024. Let's take a look at the abstract to understand what this paper is really about. The goal of this paper is to design an adaptive finite time controller for microgrids that stays robust against time delay cyber attacks. These attacks disrupt the time synchronization of data and mess with frequency control. The authors modeled the microgrid using fractional order calculus and then designed a terminal sliding mode controller that converges fast and adapts online to unknown disturbances. Now let's take a look at what the microgrid's structure actually looks like. This figure shows the overall structure of a typical microgrid. Electric vehicles, diesel generator, wind turbine, solar PV, and the storage systems, all connected through communication gateways to the control center and SCADA. Now let's take a look at how an attacker can actually get into this system. This diagram shows how attackers can inject delays into the system by hijacking protocols like MMS, Goose, and SV, or even by manipulating the GPS signal to break time synchronization. Now let's take a look at why timing matters so much here. This table lists the strict timing requirements for different types of control messages. For example, rotation information needs to arrive within milliseconds. Any delay behind these limits can destabilize the whole system. Now let's take a look at how the authors modeled the system under attack. This block diagram shows the full control framework: solar, wind, diesel, and battery storage feeding into the fractional order model, with the controller working to reject the delay attacks effect. Now let's take a look at how this control algorithm is actually computed step by step. This flowchart walks through the algorithm, from defining the system model to computing the sliding surface, to updating the adaptive law and the final control signal. Before jumping into the results, let's take a look at the parameters used in the simulation. This table lists the technical parameters of the simulated system: time constants for the diesel generator, PV, wind turbine, battery, and EV. Now let's take a look at how the power sources actually behave in the simulation. These plots show the simulated PV output, wind output, and load demand, all modeled with random fluctuations to make the test more realistic. Now let's take a look at the data behind that randomness. This table gives the parameters used to generate that random power and load behavior. Now let's take a look at the actual results, starting with what happens to the control commands under attacks. The black curve shows the delayed control command caused by the cyber attack. The red curve shows the corrected command once the proposed method kicks in. You can see it successfully rejects the delay. Now let's take a look at how that translates to the diesel generator's actual output. This compares the diesel generator's output with no controller versus with the proposed method under a 2-second delay attack. The proposed method clearly keeps the response much more stable. Now let's take a look at how this affects the overall system frequency. Part A shows frequency fluctuations under 3 seconds delay attack. Part B pushes it further, testing delays up to 10 seconds, and shows the method stays stable up to 7.3 seconds of delay. Now let's take a look at how this compares to other published methods. Here, the proposed method's frequency fluctuation is compared against two other methods from references 17 and 23. The proposed method clearly shows smaller oscillations. Now let's take a look at the exact numbers behind this comparison. This bar chart and table compare overshoot and undershoot across all three methods. The proposed method has the lowest value in both, meaning it's more accurate and more stable. Now let's wrap this up. This paper presents an adaptive finite-time terminal sliding mode controller for fractional order microgrids that stays robust against time delay cyber attacks. It reduces overshoot and undershoot compared to existing methods and can tolerate delays of up to roughly 7 seconds while keeping the system stable. I'll be covering more papers related to this field, so stay with us.